Friday, which means, as much as I hate this, okay, unit test Monday and Tuesday. I hate giving tests on, or after a weekend, but it looks like that's how it's going to work out for this unit, okay? But the good thing is, maybe a good thing, some of us are going to be excited about this, we're getting the unit test in before the end of the quarter, because the end of the quarter is happening next week. So this is going to be like the last big thing on there, which could be a positive for some of you, okay, depending on how we do. I think, at least the vibe I'm getting, is we're feeling a lot more confident with this unit than we did the last one. So this unit test is going to hopefully be a good boost for some of us, okay, because we're going to get it in on time, okay? I forget how far we got on Friday with this trig example, looking at increasing and decreasing. Did we fill out the chart completely? No? Did I fill in the last one prematurely for you guys? Okay, if you were to pick a radian value between 4 pi over 3 and 2 pi and plug it into the derivative, you would get a positive value. So we know the original function is increasing on that interval. So the directions for these few questions we were looking at on Friday was we want to determine the intervals where the original function f of x, in this case is, or f of theta, is increasing and decreasing. We also want to label and find the ordered pairs of any maxes or mins, those high points or low points. So based off that chart, can we identify of these critical points that we found on Friday? Maybe one of them's a min, one of them's a max, maybe one of them's a level. Okay, that's another option as well. But what do you think? Based off the chart, can we identify what is 2 pi over 3 and 4 pi over 3? Good, Braden?
2 pi over 3 is a max and 4 pi over 3 is a min.
Perfect. Okay, we'll get to the justifications in a second, but let's go ahead and start with the justifications for increasing and decreasing. So f of theta is increasing on the intervals from 0 to 2 pi over 3 and 4 pi over 3 to 2 pi because based off of our little chart, how did you know you could write increasing in those boxes? Good, Braden?
F prime of theta is positive.
The slope, yep, f prime of theta is positive. Good. Okay, so another similar statement, this time for decreasing. F of theta is decreasing on 2 pi over 3 to 4 pi over 3 because f prime of theta is negative. All right, so that answers our increasing and decreasing intervals with justification. We can then move on to maxes and mins. We said f of theta has a max at the x value of 2 pi over 3 because, now Braden, I'm going to come back to you because you told us you have a max there. How did you know?
F prime of theta goes from positive to negative.
Okay, so you could use the derivative information. The derivative changes from positive to negative. You could use the original function information. Okay, f of theta changes from increasing to decreasing. It doesn't matter, they all mean the same thing. You just need to choose which one you want to label. Maybe the derivative changes positive to negative. I'll abbreviate there, positive to negative. We have the original function, which means we should be able to figure out the height of this maximum. Because we know the x location, we should be able to use that to figure out the y location. So if we were to plug in 2 pi over 3 into the original function at the top, okay, I'm not going to move my paper, but you guys can reference it at the top. If you plug in 2 pi over 3 into theta at the very beginning. That would be 2 pi over 3. But then we have to add sine of 2 pi over 3. So unit circle, you may have to reference it. It's on page 10. What is the sine value at 2 pi over 3? Or maybe some of us know it. Square root of 3 over 2. Okay, so that's the sine value, square root of 3 over 2. But we have to multiply that by 2 based off of the original function. So the 2's would cancel out, and we would just be left with the square root of 3. So I know it looks weird, but whatever that decimal value is, that's the height of your maximum. So we'll label that as our maximum value. Let's go ahead and write a similar statement, but for a minimum that we identified. So f of theta has a min at the x value of 4 pi over 3 because f prime changes, we'll say negative to positive. And since we have the original function at our disposal, we'll go ahead and use it to figure out the height of the minimum. We're going to plug in 4 pi over 3. So 4 pi over 3 into the theta is good to go. Then we got to figure out what is sine of 4 pi over 3 on our unit circle. I think it's the square root of 3 over 2, but it's negative. You're in a different quadrant. So negative square root of 3 over 2 times 2 based off the original function at the top. So the 2's would cancel and we'd be left with a negative square root of 3. So there's the minimum height. It might not be the lowest height, okay, but it is a low point or low height on the graph. Coming back to us from last week? Good, good, good. All right, so the section we're going to start today, I really wouldn't call it anything new. If you look at the title of it, it's just solidifying the concept of a derivative in tangent line for us. We're just going to take a look at a bunch more examples and questions and wordings and phrases for us to really get comfortable with the derivative, with the slope of a tangent line. So some of these questions might look familiar or at least sound familiar because this is going to be, in a sense, extra practice, almost like preparation for your partner quiz. Okay? So, on page 127, picture to the right is the graph of a quadratic function g of x. So notice how it's named. Okay, g of x is an original function like f of x. They just call it g in this case. So we'll label it g of x. Number 1, find g prime of negative 4 and explain what this value represents in terms of the graph. So, what does g prime of negative 4 mean? What does that notation represent? What on earth are we trying to find? Can you decipher or interpret the problem, the wording? Maybe we'll just start with the g prime part. G prime, what does that mean? The derivative or slope of the g equation. And what's the negative 4 mean? Or what does that represent? Good, Braden?
Point.
A point. It's an x location on your graph. So we're trying to find the slope of the g graph. Notice how this is the g graph. We're trying to find the slope of the g graph at negative 4. How do you want to try to do that? We have options. Yeah?
First find the g prime of x equation.
Okay, so notice how we have like two different pieces of information here. We have the equation of g, which is nice, but we also have the graph of g. Okay, so we have two pieces to go off of. We can either tackle the equation part, okay, find the derivative using our shortcuts, like the power rule, or you could try to tackle the graph. Okay, we know that the derivative represents the slope of the tangent line. Now, if you were to go to that -4 spot and draw a tangent line as best you can, it would look something like that. But what do you think would be more accurate? Do you think finding the equation of the derivative would be more accurate, or finding the slope of that tangent line would be more accurate? Because they're just telling us to find the derivative. They're not telling us how. We got to figure out which one would be more appropriate. Probably the equation, right? Because our tangent lines, every one of ours is going to be slightly off, right? Because we're freehanding it. But if we tackle the equation, we're all using the same equation, so we're all going to get the same result. If we're going to find the derivative of this equation, though, what do we have to do? If we're going to use our shortcut, our power rule, what does it have to look like? Can we describe it? Do we know the wording or phrasing? Yeah.
Polynomial.
A polynomial, right. We need to get rid of parentheses, okay? No fractions, at least with x's, no fractions. So if we were to write x plus 2 twice and go through a FOIL process, we would have x squared plus 4x plus 4. We still have the 1/2 out front. And let's go ahead and distribute in that 1/2. And looks like we can combine some like terms on the end. Okay, so this is just g of x rewritten in polynomial form. We did no calculus there. That was just algebra. Okay, now that it's in polynomial form, let's use our calculus, our derivative shortcut rules. Can we apply the power rule real quick? We getting good at that? Good, Stevie?
X plus 2.
X plus 2, perfect. All right, so they want us to find g prime of -4. So now that we know what g prime is, the derivative equation, let's plug in -4. And looks like we'll get -2. So that's the value, okay, the number answer for g prime of -4. They also want us to explain what this number of -2 represents in terms of the graph of g of x. So where is this -2 idea showing up on the graph? Can we justify it or explain it? Good, Stevie?
The slope of the tangent line is -4.
All right, the slope of the tangent line specifically at the location of -4. Good. Perfect, perfect. Let's check out 2. Find the equation of the tangent line drawn to the graph of g of x at -4. So we still have the same location, okay, this x location of -4. Sketch a graph of this tangent line on the grid above. Okay, I kind of got ahead of myself and already did that. Okay, just thinking about it from number 1 might have been a good idea to draw it eventually. So there's the tangent line drawn. We want to find the equation. So what information do we need to find to help us with the equation? Yeah.
Slope and a point.
Slope and a point. Where's the slope come from? Yeah. Derivative. We are on a roll. Point comes from? You're my little minions, yeah.
Original.
Our original, my little robots. Beating it into your brain. Okay. So we're going to plug in -4, that's our tangent location, into the derivative and the original. Let's see, we already did that before, right? For the slope, we got -2. If you were to plug in -4 into the original, Now you could either plug it into the equation, but you also have a graph. Choose which one you think is easier to work with. I think you'd get -2. All right, so tangent equation, y minus y1, actually changed to +2 from that point, equals our slope times x minus x1. Our x location is that point of tangency. Nothing new, right? Solidifying the concept. We're just doing a few more problems, letting it sink in. All right, 3 might be a little new for us. Okay. Using the equation of the tangent line, find the value of y when x is -0.3. So how do you want to use this equation we found to help us with that first part? How can we find the value of y? That's right, Braden. Just plug it in. Right? Okay. So in our equation there, let's go ahead and plug in -3.9. We can do this without a calculator. -3.9 plus 4. .1. 0.1 times -2. -0.2. Subtract the 2 over. -2.2. All right, no calculator needed for that one. Good to go. Second part of the question, then find the value of g of -3.9. What's that asking or telling us to do? Yeah.
Plug it back into the original.
Plug it into the original. All right, so we're going to plug in -3.9 into the equation at the top. You may need a calculator for this one, so if you have one handy, go ahead and bust it out. Any takers? Calculator people, have it handy. Go to Braden.
-2.195.
195. Okay. All right, so let's take a look at 4. What do you notice about the values of these two results from number 3? Okay, we had 2 answers. What does this imply? What does this imply about how the equation of a tangent line might be used? So we've been finding equations of tangent lines for a few days now, maybe a week or so, okay? So I'm trying to get to the point of why are we doing this, okay? Why is it useful to find the equation? Let's just tackle the first question. What do you notice about these two values? Yeah. They're basically the same thing, right? They're extremely close together, okay? So why do you think writing the equation of a tangent line might be useful? If these are basically the same thing, they are pretty darn close together, why go through a tangent line process? Why write the equation? I'll play the Jeopardy theme song. Or some crickets. Either of the two. All right, let's think about this. Did we need a calculator for this one? No. Did we need a calculator for this one? Yeah, we probably could have done it without a calculator, right? Okay? It would have taken us some time. But notice how the tangent line equation is very close, or the tangent line approximation is really close to the actual approximation. Okay, I want you to take a look at the graph at the top, or maybe I'll just draw an example down here. Okay, let's say this is the original function. okay, f of x, g of x, whatever you want to write. And we plot some point and we draw a tangent line. If I were to pick a point, did you guys notice how negative 3.9 was really close to the negative 4 that we've been using, right? So if I pick an x location really close to that point of tangency, maybe right there, okay, isn't the tangent line point extremely close to that actual one, no matter which direction you go in, right? So the purpose of the tangent line is it is a way for us to approximate function values without necessarily needing to know the function itself, okay? Isn't this answer close to this one? And the only way we got this answer was by using the actual function. If you didn't know the actual function, you only knew the tangent line equation, you would be extremely close, right? Okay, so the tangent line is a good approximation when the function equation might not be known. Okay, it's kind of a useful piece there. So we'll go ahead and write that down. We'll say the tangent line gives a close approximation to the actual function value. Right? We said the negative 2.2 from the tangent line was really close to the actual function answer or value of negative 2.198. Okay? We're going to add a stipulation in here. Okay? Provided that the x value is close to the tangent point. Okay? So our x value of negative 3.9 was close to the tangent point of negative 4. I hope we realize, okay, if you take a look at my kind of drawing here on the graph, if my tangent point is somewhere right there, and I were to choose something further away, for instance over here, isn't the difference between the actual function value and the tangent line bigger? That's a bigger difference than what they are here, right? So you need to, in order for it to be a good approximation, the x location in question has to be close to the tangent point. The further you get away, the less accurate you're going to be. So we're going to throw that stipulation in there, okay, provided that the x value is close. Let's think about this. This approximation of negative 2.2, was that an over or an underestimate of the actual one? Is negative 2.2 more or less than negative 2.198? You gotta think about a number line. I know negatives kind of get a little tricky. Negative 2.2, more or less than the actual? Yeah, less. Okay, so let's talk about that. Let's think about why is it a less than approximation in this case? Because in other examples, it could be greater than. Okay, so this I need you guys to write down if you have space down here. What we're going to do is think about the shape of the graph when we draw a tangent line. Okay? Because we've seen different parabolas, different curvatures going on. We're definitely going to get into this later this year. If you have kind of a regular parabola shape, this is what's referred to as concave up. I'm going to do CC for short. Okay, concave up. Basically, think about if you were to fill it with water, the water would stay in the bowl. Okay, concave up. The other one, though, is concave down. If you were to try to fill that with water, the water would fall out. Okay, so I want you to think about if you were to pick any point on this concave up graph and draw a tangent line, and maybe do the same thing on the concave down. Pick any point you want and draw a tangent line. I'll do some on the other sides just to prove my point. Where are the tangent lines located in relation to the actual graph if you're concave up. Can you describe where those tangent lines are, those blue ones, in relation to the red one, no matter which point you pick? Can you see how they're below the graph, kind of? Okay, so no matter if we pick a point to the left or to the right of this one, notice how the tangent line is going to be less than the actual graph. Okay, so if you have a concave up, your tangent line approximation is going to be smaller because your tangent line is below the actual graph. So we'll say in this case, tangent line is under estimate. And isn't that what happened in our example? If you take a look at the graph at the top, isn't it concave up? Okay, and the approximation we found was less than the actual. Okay, in the other case, if we're concave down, notice how the tangent lines are above the actual function. So we would say tangent line is an over estimate. Okay, you'll probably get a value that's more than the actual one. Does that make sense? Can we visually see that? Okay, so the tangent lines are really good function approximations. You can get really close to what the actual function value is, and you can even determine if it's an over or underestimate if you can take a look at the curvature. Is it concave up or concave down? So we might see a few more questions related to that, but I hope it makes sense. Okay, kind of clicks. All right, let's check out number 5 on the back. Pictured to the right is a graph of g of x, okay, an original function. Use the graph to help you answer the following questions. Based on the graph, at what values do you have a horizontal tangent? There's that phrase again. What does that mean, horizontal tangent? Yeah?
Relative max or min.
Relative max or min. Okay, so we're looking for a slope of 0. Maybe we'll label this g prime. Okay, we could also have a level spot. The slope is 0 at level spots. Okay, so based off the graph, where do we have a slope of 0? A max, a min, or a level location? Yeah.
Looks to be at 1.
Looks to be at 1. Okay, so x equals 1 appears to have a horizontal tangent because it said give a reason. How'd you know, Dan?
Because it levels off at that.
Levels off, specifically a maximum. We have that high point because there is a maximum. All right. Show algebraically, okay, by hand, using some algebra, perhaps some calculus, that you can figure out this same location, okay, same x value of 1. So, algebraically, we're going to have to figure out what the derivative is and set it equal to 0. So, taking a look at your original equation, okay, if we're going to use some shortcuts, because I know you guys don't want to use that limit, it has to be in polynomial form. Not exactly... It doesn't exactly look like that just yet. Can we rewrite anything? Get it to be x to a power? Yeah.
Change the square root of x to 1/2.
I like it. All right, so we'll change it. Let's go ahead and find our derivative real quick. Power rule. Looks like we'll have x to the negative 1/2 minus 1. Okay, I don't know about you, but I don't like working with negative exponents. So let's move it to the bottom, make it positive. And if you don't like working with fractional exponents, you can always turn them back into a root. So this would be 1 over the square root of x minus 1. Okay, so there's our derivative. We're going to set it equal to 0 to figure out those horizontal tangent locations. How do you guys want to solve for x? Think some algebra steps. We got to move some terms. You guys want to add the 1 over? All right. Variable in the bottom. This always gets people. What do you want to do from there? Yeah.
Can't you just substitute the 1 in?
This one?
Yeah.
We're trying to get this as an answer. We're trying to show that guess we had was correct. What do you think, Stevie?
Multiply it over.
Multiplied over, yeah. You can always get rid of a fraction by multiplying the denominator over. So 1 times the square root of x, just the square root of x. Square both sides. Looks like we get 1. Okay, so notice how that guess we had based off the graph is correct. Okay, algebraically, mathematically, using the calculus, it's confirmed. Okay, so that guess we had was perfect. Good, good, good. All right, on what intervals is the derivative less than 0? What should we be looking for? What does that notation even mean? Yeah.
Positive slope. Right?
Less than 0.
Oh, negative slope.
Negative slope. Okay, so on this graph of the original function, if you were to draw in some tangent lines, where would their slopes be negative? Let's see, we had a level slope at 1. What do you think, Vinny? 1 to infinity. Good, because we said the slope, or g prime of x, the derivative is, or sorry, g of x, the original function. How'd you know it was from 1 to infinity, Vinny?
Well, one's the max and coming down.
The original graph, right, is going down after that. So g of x is decreasing. Okay. Very similar question for 7. On what intervals is the slope bigger than 0? AKA positive. Good, Stevie?
0 to 1.
0 to 1. Really small interval. Yeah, because g of x is increasing. If you were to try to draw a tangent line between 0 and 1, I know it's a little small, but it would be positive going up. All right, maybe we can tackle the next one before the bell rings. On what values, or for what values of x is the slope of the tangent line equal to 0? Or sorry, 2, equal to 2. What's that asking us to find or set up? Slope of tangent, aka, yeah, derivative. So we need the derivative to equal 2. We'll check that out tomorrow. We doing okay? Is this kind of review stuff for us? Except for the tangent line approximations, okay? But I think we're doing really good.